Welcome back to our course MN22062 Drone Technology. I am Ranjit and we are continuing our journey through Unit 3 Advanced Drone Operation and Control System. Today we'll be building on the concept from our last session to explore some of the most advanced topic. In our previous lecture, we made a critical transition from theoretical world of perfect model into complex of real world operation. We began by analyzing the significant impact of wind on MAV flight, introducing the wind triangle and the different velocity vector we must consider. From there, we conducted through a tour of MAV onboard sensor suite. We examined the principal measurement and challenge challenges associated with the accelerometer, rate gyros, pressure sensor, magnetometer, and the global positioning system. A key theme that emerged was that each sensor is imperfect. They are they all suffer from noise, bias, and other sorts of error. This leads to the crucial topic of estimation, where we establish the need of intelligent process and combine data from multiple sources. We concluded by looking at the simplest estimate technique like low pass filtering and then introduces the powerful concept of dynamic observer, which use a model of the system's physics to predict and correct its state setting. The stage for today's discussion will take the foundation knowledge and apply it to advanced algorithms and design methodologies that are used in modern autopilot. We will begin with a deeper dive into extended Kalman filter or EKF, which is the predominant algorithm used in MAVs for state estimation. We'll explore how it handles the nonlinear inherent in MAV dynamics and how it is applied to the specific problem of altitude and navigation estimation. Once we have the robustic state estimate, the next logical step is to use it for control. Therefore, the control part of our lecture will focus on autopilot design, specifically a powerful technique called as successive loop closure. We see how complex control problems can be broken down into a series of nested inner and outer loop, controlling everything from altitude to altitude and course. Finally, we will move to the highest level of autonomy, motion planning. We will define what it means for a MAV to plan its own path and explore some of the classic algorithms like RRTS that enables drone to navigate intelligently through complex and cluttery environment. By the end of this session, you will see how all the pieces we have assembling dynamics, sensors, estimation, and control come together to create a truly autonomous system. Our last discussion concluded with the introduction of dynamic observer theory, a powerful method for estimation that uses a model of system physics. Today, we'll focus on the most widely used implementation of that theory in robotics and aerospace, the extended Kalman filter. The extended Kalman filter is an extension of Kalman filter for nonlinear system. The original Kalman filter is a landmark achievement in estimation theory, but it has one major limitation. It only works for systems whose dynamics and measurement are described by linear equation. Unfortunately, the physics governing aircraft flight are highly nonlinear. The EKF is an indigenous adaptation that allows us to apply the power of Kalman filter to these real-world nonlinear problem. At its core, the EKF's purpose is to estimate the state of dynamic system from a series of noisy measurements. This is precisely the problem we need to solve for our MAVs. We have a dynamic system, the drone, and a series of noisy measurements from its sensor. And we need to produce the best possible estimate of its cruising, such as its altitude, velocity, and position. The key innovation of the EKF is how it handles the nonlinearity. Instead of solving the nonlinear problem directly, it cleverly sidesteps it. The EKF uses linearization around the current estimate to apply the standard Kalman filter. The diagram on the slide provides a great illustration of this process, which it is called as passing Gaussian through linearized approximation. Imagine the system has a belief about this current state, represented by the bell curve on the left. To predict the next state, this belief must be passed through a nonlinear function. EKF approximates these curves with a straight line, a tangent, at the point of the current uh, best estimate. It uses this simplified linear model to project belief forward, resulting in new adapted belief about the state. Mathematically, the EKF handles nonlinear state transition and observation model through Taylor series expansion and Jacobian's matrix. The first order Taylor series is the tool used to create the linear approximation, and the Jacobian's matrix is the result of this process. This technique is not just an academic exercise, it is absolutely critical for the navigation, tracking, and control system. In fact, the EKF is widely used in MAVs, micro air vehicle, for state estimation. It is the workhorse algorithm that runs at the heart of the most modern autopilots, fusing the data from IMUs, GPS, and other sensors to provide a single, robust estimate of the drone complex state. Now that we have the highest level understanding of what the extended Kalman filter is, let's look more closer at how it operates. The EKF is specifically designed for addressing nonlinearity in system propagation and measurement model. This means it can handle both the complex physics of the drone motion and the nonlinear way in which its sensor relates to its state. The EKF accomplishes this through a step-by-step process, prediction and updation. The first phase is the prediction step. In this step, the filters use its internal model of MAV's dynamics to project the current state forward in time. It propagates the state estimate and error convergence using non-linear model and its Jacobian matrix, especially based on the last known state and the command sent to the motor. It makes an educated guess about where the drone is now and how it is oriented. Crucially, it also predicts it is now uncertain, known as the error convergence. It also it is also predict that it is perfect and uncertain will grow over time without new information. The second phase is the measurement update. This occurs when the new piece of the data arrives from the sensor, like GPS or an accelerometer. The filter then corrects the state estimate and, and a covariance based on the sensor measurement and the Jacobian of the measured model. Compare its prediction from the last step with the ac- accurate measurement. If the measurement is close to the prediction, the filter becomes more confident in its estimate and reduce its uncertainty. If the measurement is significantly different, the filter adjusts its estimate, weighting the new measurement against its predicted based on how noise it is believed the sensor to be. This constant cycle of prediction and correction is what allows the EKF to track the true state of the system over time. Both of these systems are made possible through the process of linearization. The EKF uses first order Taylor series approximation around the current estimate to create a linear version of non-linear model. This allows the powerful mathematics of the original Kalman filter to be applied. The filter is that provides a balance between computational efficiency and accuracy for moderately non-linear system. It may not be as precise as more advanced filter, but it is a highly efficient, making it perfect for the embedded processor on MAVs. The AHRS evolution diagram on the slide shows this practically. Early autopilot firmware like Copter 3.21 uses simple methods like TCM and inertia NAV. However, later version processed to use EKF1, EKF2, and now we are currently at EKF3, demonstrating the industry's wide adaptation and continuous improvement of EKF as the standard of MAV state estimation. Now that we have established the theory behind EKF, let's look at this first and the most critical application in the MAVs, altitude estimation. This is the process of figuring out the drone's orientation in space, which is fundamentally to all aspects of its flight. The primary application of this specific EKF is that it estimates the roll and pitch angle of the MAV. While some observers also estimate, yeah, the core task of stability is getting a fast and accurate reading of the roll and pitch angle. The variables that the filter is actively trying to figure out are controlled in what we call it as the state vector. For this task, the state vector typically includes roll, pitch, and their rate, which can be mathematically written as x equal to chi theta p and q multiplied by t. This means the filter is simultaneously producing an estimate for four values: current roll angle, current pitch angle, current roll rate, and current pitch rate. To produce these estimates, the filter intelligently combines the data from two different states. The model integration shows how it works. The EKF uses the angular rate measurement for state propagation. This means it takes the high speed data from the onboard gyroscope, the P and Q rates, and uses them in predicting step to project the altitude forward in time. However, because gyros drift, this prediction alone won't quickly become uh, won't quickly become accurate. Therefore, the filter also uses accelerometer measurement as output equation. The accelerometer provides a stable, long-term reference to the direction of gravity. In the update step, the filter compass into gyro-based prediction to the gravity vector measured by the accelerometer and uses the difference to correct from any accumulated drift. The result of the is sensor fusion is majorly improving the accuracy over simpler techniques. The EKF provide significant better estimate during accelerated flight compared to simple method. The simpler method that rely heavily on accelerometer can easily confuse during turn or fast forward flight because the force from acceleration combined with the force of gravity makes it difficult to know which way it is truly down. Because the EKF has a dynamic model, it can anticipate and account for this acceleration, maintaining a much more reliable altitude estimate even in aggressive maneuvers. Yes, ultimately, this robust and accurate estimation is essential for stable flight control and navigation system in MAVs. Without a trustworthy sense of this own altitude, a MAV cannot simply fly stable or navigate efficiently. Having seen how the extended Kalman filter is applied to the altitude estimate, we can now expand its scope to the even more comprehensive task of full MAV's navigation. This involves not just knowing how the drone is oriented, but also where it is going, and what environmental forces are acting upon it. The application of navigating EKF is to estimate a much larger set of variables. It estimates position, PN and PE, ground speed, which is VG, course, which is mentioned by X, wind, which is mentioned by WN and WE, and heading, which is mentioned by the letter chi. This state vector is incredibly rich. It includes MAV's position in north and east coordinates, its speed and direction of travel to the ground, the north and the east component of west vector, and its angle or heading. By estimating all these states simultaneously, the filter can build a complete picture of MAV's situation. This comprehensive estimate is achieved through a process that can be thought as an advanced GPS smoothing. The filter integrates GPS position, ground speed, and control measurement like with a nonlinear propagation model. In this updated step, in this updated step, the EKF uses the measurement from the GPS receiver. However, in between these relative slow GPS update, the filter uses its internal physics model driven by high frequency data from inertial sensor to propagate the state estimate forward in time. This process fills in the gap between the GPS reader and filters out the noise, resulting in smooth, high rate navigation solution. The enhanced performance of this approach is significant. The EKF produces much better navigation estimate than the simple low pass filter, especially in the dynamic missions. A simple filter on the GPS would be sluggish and lag behind the drone's actual movement, where the EKF's prediction model allows it to generate a much more responsive and accurate estimate during maneuvers. One of the most powerful features of this type of filter is its wind estimation capacities. By comparing the MAV's velocity through the air with this velocity over ground, EKF solved for the wind vector. This is a crucial capacity for path planning and energy efficient flight in outdoor. Knowing the wind allows the drone to fly more precise path and conserve energy. Ultimately, this sophisticated estimation enables robust autonomous navigation even in a challenging weather condition. Now that we have the robust state estimate from our extended Kalman filter, the next logical question is how do we use the information to actually control the MAVs? This brings us to the fundamental design philosophy of modern autopilot, a technique known as successive loop closure. The principle of this approach is elegant and powerful. It involves designing multiple single feedback loops in succession rather than one complete system. Instead of attempting to create a single monolithic control that handles every aspect of flight time simultaneously, we break the problem down into a nested series of simple control loops. Think of it as a hierarchy of control. The innermost, faster loop handles the most basic stabilization, and each successive outer loop gives command to one inside it. This cascaded structure is classic and highly effectively controlled strategy. The key that makes this approach work is concept called bandwidth separation. The rule is that inner loop operates at higher bandwidth, 10 to 15 times faster than the outer loop. Here, the bandwidth refers to how quickly a loop can react to changes. Innermost, which might be controlling the angular rates of the MAV, needs to be extremely fast to provide stability. The next loop out which controls the drone altitude. Its roll pitch angles can be slower because it relies on the inner loop to handle the rapid fire stabilization. The outermost loop, which might control the MAV's position or altitude, can be slower still. This separation is crucial because it allows us to design and tune each independently. As the slower outer loop perceives the faster inner loop as a single, well-behaved system, they can simply command. The building blocks of each of these individual loops are known as compensators. A flight control typically uses PID or lead lag compensators. PID controllers are the workhorse of the control world. They calculate a control output based on current error, the accumulation of the past error, and predicted future error, allowing for a remarkable balance of responsiveness and stability. Increased sophistication of CPU used in flight controller as shown in the figure, depicting the evolution of flight controller has enabled more advanced implication of these control systems. Ultimately, this approaches simplifies design, tuning, and implementation while providing robust performance across different flight conditions. By breaking a complex problem into a series of manageable, simple ones, we can build autopilot that are easier to develop and more reliable in the air. Now that we have introduced the design philosophy of successive loop closure, let's look at the concrete example of how it is implemented. This slide details the structure of typical PID, the lateral autopilot, which is responsible for controlling the MAV's roll and yaw motion to follow a specific path. The architecture is built around a fine inner loop and a slower outer loop. The inner loop is the roll altitude loop. As the name suggests, its inner loop controls roll angle chi and the roll rate p. Its sole purpose is to achieve and hold a specific bank angle as quickly as accurately as possible. It uses the primary roll control surface, the aileron alpha, to do this. This loop runs at a very high frequency, constantly making tiny adjustments to make the MAVs stabilized at the commanded roll angle, detecting the disturbance from things like wind gusts. While commands to this inner loop is the course hold loop. This is the outer loop, and its job is to regulate course angle x. The course angle is actually directing the MAV is traveling over the ground. This loop is concerned with navigation, making sure the drone is flying towards its intended pathway. It achieves this not by controlling the ailerons directly, but by commanding the roll angle. For instance, if the autopilot determines that it needs to turn right to back on the course loop will simply send a command like roll to 20 degree to inner roll altitude loop. A fast, stable inner loop that executes this command precisely. This separation of duties is the essence of successive loop closure. For some more advanced fixed-wing aircraft, an additional optional loop might be included as side slip hold. This loop's purpose is to ensure the aircraft is flying cleanly through the air without skidding sideways. It uses rudder delta R to maintain zero slip beta if equipped, resulting in a more efficient and coordinated run. By layering these simple controllers, we create a highly efficient system. As the slide concludes, the nested loop structure provides stability and robustness against disturbance while maintaining desired flight path. A fast inner loop handles the immediate stability, while the slower outer loop focuses on the overall navigational goal. This elegant design simplifies development and tuning and results in a very robust autopilot. Just as we use a nested loop structure for a lateral control, we apply the very same design principle to manage the aircraft's longitudinal motion, that is, its pitch, altitude, and forward speed. This slide breaks down the components of typical PID control for longitudinal autopilot. The architecture is once again built around the fast inner loop and the slow outer loop, as shown in the block diagram. The foundation of longitudinal stability is the pitch altitude control loop. This inner loop controls pitch angle theta during the elevator. Its one and only job is to hold the aircraft nose at a specific pitch angle that is commanded by the outer loop. It runs at high frequency using the elevator to make rapid adjustment to maintain this angle, thereby providing the core pitch stability for the MAV. The next layer of control is the altitude hold using commanded pitch loop. This is the outer loop, and its purpose is to regulate altitude H by commanding pitch theta C. This is a perfect example of successive loop closure. If the autopilot determines that MAV is below its desired altitude, this outer loop doesn't command the elevator directly. Instead, it calculates the required nose up pitch command and sends that to the inner loop. A fast and stable inner loop then takes over to execute the command, causing the aircraft to climb. Controlling airspeed is bit more nuanced as the relationship between pitch and throttle changes depends on the phase of the flight. There are different airspeed control methods. Often, the autopilot is using commanded pitch theta c in climb and descent zone to manage speed while setting the throttle to full or idle. Conversely, it will be using throttle delta t in altitude hold zone to regulate speed, while the pitch is being used to maintain constant altitude. When designing and tuning these nested PID loop, engineers must consider several key design parameters. These include actuator saturation limit, a desired damping ratio, to control the responsive and principle of bandwidth separation to ensure the inner loop are always significantly faster than the outer loop they support.
As we saw in the previous slide, the best way to control the aircraft's altitude and the airspeed can change depending on what it is trying to do. To manage the complexity, Autopilot uses a logical structure called the state machine. This slide provides an overview of typical altitude control state for MAVs. The core idea is that different flight regime define control strategies for different phases of flight. A single state set of control is not optimum for every situation. So the autopilot switches between different modes or regimes as needed. To look at the primary flight regimes for longitudinal control, first is the takeoff and climb. During this phase, the objective is to gain altitude efficiently. The control strategy is full throttle with pitch control at speed. The system applies maximum power to climb and uses the elevator to adjust the pitch angle to maintain the most efficient climb speed. Once the MAV reaches the target altitude, its transition is to hold altitude regime. Here, the control logic inverts. The primary goal is to maintain constant altitude, so pitch control altitude, while throttle regulates airspeed. The elevator makes fine adjustment to the pitch angle to hold the commanded height, and the pilot or navigation system now uses the throttle to control the forward speed. Finally, when it is time to come down, the autopilot enters the descent mode. In this phase, the strategy is reduced throttle with pitch controlling airspeed. The power is cut back to allow MAV to descend, and the pitch is once again used to control the forward speed during the descent. The critical part of this decision design is managing the handoff between the different modes. Dynamic mode switching is logic that ensure smooth transition between flight regimes. These transitions are typically triggered based on the altitude error and vertical rate. For example, as the MAV in the climb approaches its target altitude, the altitude error becomes small and the state machine will command a smooth transition into the altitude hold mode. Underneath this high-level logic, the implementation uses PID loop converter to discrete time with anti-wind-up scheme. This robust combination of high-level state logic and low-level PID control allows the MAV to manage its flight safely and efficiently through all phases of a mission.
Now we have reached the highest level of our autonomy stack. We have discussed how a MAV estimate its state and how its autopilot use the state to achieve stable flight. Now we must answer the question how how does the MAV decide where to go in the first place? This is the domain of motion planning. Effective motion planning is essential for autonomy, autonomous navigation in complex environment. Definition of motion planning is the process of computing explicit path or trajectory for MAVs. This is the onboard intelligence that takes a high level goal like fly to other side of the building and compute a safe, flyable and efficient route to get there, taking into account obstacle the drone performs limit and these constraints. There are broadly two philosophical approach to this problem. The first is deliberative planning, which is planning based on global knowledge. This is like using detailed map to plan an entire journey before you start. The algorithm has complex picture of environment and can compute global optimal path. The second approach is reactive planning, which involves reacting to local sensor information. This is more like navigating without a map, using only what you see directly in front of you to avoid obstacle and move forward towards your goal. Most advanced MAV uses hybrid approach, using deliberate planner to find the overall route and reactive layer for immediate collision avoidance. Designing motion planner for MAVs comes with a unique set of challenges. One of the biggest MAV specific challenge is need for computational efficiency algorithm. The MAV has limited onboard processing power, so it can't afford uh, to spend a second or minute calculating a path. The path must be nearly instantaneous. Furthermore, the MAV must operate in a dynamic environment. The world is not static. Other vehicle, people, or object may be moving, and the planner must be able to update its path in the real time to avoid them. Finally, a planner must be robust to the inherent uncertainty in the model. The MAV's knowledge of its own position and the location of the obstacle is never perfectly accurate, and the motion planner must be able to generate paths that are even with this uncertain decision. Hope that we laid the foundation and explored the challenge of motion planning. It's time to dive into some of the advanced algorithms that are used to tackle these problems in practice. They are not just theoretical tools, they are the core techniques that allows micro aerial vehicles or MAV to autonomously navigate complex environments. Think forest, urban canyon, or cluttery outdoor space. Let's begin with the classical approach that has been around for some times, yet still holds strong in many path planning applications. Voronoi graph. Let's start with the concept. Voronoi graph works by dividing the environment into convex region or cells. The edge of the cell are positioned exactly halfway between the obstacle in the environment. Think of this way. Imagine you are in a field full of rocks. Obstacle. If you were to draw a line such that every point of the line is the same distance from the two near rocks, you will end up with something like a Voronoi diagram. The result is a network of paths that maximize the clearance from any obstacle, which is very desirable property when you are flying a drone through tight space. Technique is particularly useful in uh, con- congested, particularly useful in congested environment. For example, in airspace with a lot of point like obstacle, like trees or towers, because it inherently find the safest possible path. It is well suited for scenario where obstacle avoidance is the top priority. Next, we'll look at the most modern and widely used algorithm, especially in robotics and algorithm and autonomous vehicle, the rapid exploration random tree or RTT, RRT, random tree or rapid exploring random tree. So, what is the big idea behind RRT? The core concept is that sampling based algorithm rather than exhaustive search the entire space, which can be computationally expensive. The RRT randomly samples the environment and builds a tree of possible paths. Here's how it works. First, the algorithm picks a random point in the space. Then it finds the closest node in which the current tree of known path. Finally, it extends the tree a small step towards that random point. This process is repeated again and again, rapidly growing a network of paths from the start location. Over the time, one of the branch will likely connect with the goal region, providing a feasible path. What provides what powerful about our RRT is how quickly it can cover a large complex space, especially when compared to deterministic approach. However, the trade-off is that the path it finds are often rough or inefficient. The next method uh, is the RRT's extension. To deal with those jagged, less that ideal path, we turn to extend post-processing technique. One key extension is called path smoothing. After RRT find a valid path, path smoothing is applied to remove unnecessary immediate points. This makes the route shorter, cleaner, and more efficient for the drone to actually follow. Without smoothing, the drone might be making constant sharp turns, which isn't ideal for flight stability or battery life. Another important extension, especially relevant for MAV's operation in the outdoor environment, is the 3D terrain planning. Instead of planning it in a flat 2D space, this technique allows us to extend RRT into 3D, taking into account altitude variation and terrain constraint. This is essential when navigating over hills, building, or through valley. The algorithm ensures that the waypoint are chosen that the MAVs maintain safe and efficient flight in in a vertically varying environment. We will move beyond the simple idea of a remote controlled aircraft and explore the complex layered system that enables true autonomy. We will we have covered the entire stack of technology from the sensor that perceives the world to the algorithm that makes sense of the data, and finally to the advanced control and planning that allows a drone to execute complex mission on its own. Our journey begins with the foundation of all autonomous operation, the sensor. The drone's ability is to navigate and stabilize itself, starting with its inertial system. At the core of this is the inertial measurement unit (IMU), which typically contains two sensors. First, accelerometer are the fundamental device that measure specific force, which is the combination of aircraft's own acceleration and constant pull of gravity. By sensing these vector force, the drone can determine which way is down. The second component is the rate gyroscope, which is essential for measuring drone's angular velocity. It tells the autopilot how fast the drone is rotating about its roll, pitch, and yaw axis. This high-speed rotational feedback is the lifeblood of the drone's stability system. While the IMU provides the core of self-awareness, it needs external reference to navigate the world. This is where the broader suite of navigational sensor comes in. A magnetometer acts as a digital compass, detecting the Earth's magnetic field to provide the drone with a sense of heading or direction. However, this reading is susceptible to interference from the drone's own electronics, requiring careful calibration and mounting. Next, pressure sensor provides critical data for altitude and airspeed. An absolute pressure sensor or a barometer measures ambient atmospheric pressure to determine the drone altitude above the ground. Different pressure sensors, often part of a pilot's static system, measure dynamic pressure to calculate the drone's speed relative to the air mass, which is crucial for efficient flight and stall prevention. The sensor that truly unlocks long-range autonomy navigation is global position or the GPS. The GPS provides the MAV with an absolute position anywhere on Earth, which enabling the technology for further features like waypoint following and automatic return to home feature. It works by triangulating its position from the signal of least four satellites. However, the GPS accuracy is affected by factors like atmospheric delay and geometrical arrangement of the satellite, a concept known as dilution of precision. To operate where the GPS is unavailable, such as indoor or in dense urban canyon, drones are increasingly turning to camera-based or mission-guided navigation. By processing a video stream, a drone can track features in the environment to reduce its motion and build a map of its surrounding. A technique inspired by biological vision system found in the nature. Now, having this rich suite of sensor presents a new challenge. Every sensor is imperfect. They all suffer from noise, bias, and drift. This is why the next layer of our autonomic stack is state estimation. State estimation is the process of taking all this noisy, incomplete data from multiple sources and fuse into a single, accurate, and reliable estimate of the drone's true state, its accuracy, velocity, and position. The workhorse algorithm for this task is the extended Kalman filter, or the EKF. The physics of the drone flight are non-linear, and the EKF is a powerful tool that can handle by using linearization around its current best guess to apply principle of optimal Kalman filter. It operates in the constant two-step cycle. A prediction step where it uses physical model to predict the drone's new state and an upset, where it uses tensor measurement to correct its prediction. This is particularly critical for altitude uh, altitude estimation, where EKF uses the sparse but drifty data from the gyroscope with the stable but noisy data from the accelerometer to produce a clean altitude estimate that is robust even during aggressive maneuvers. Once we have a reliable state estimate, we can finally act on it. This brings us to the advanced flight control. Ron operate using different flight mode managed by a state machine that switches control strategically depend on the phase of the flight, such as takeoff, altitude hold, or descent. The underlying control mechanism is a design philosophy called successive loop closure, where we create a nested hierarchy of simple feedback loop rather than one single complex controller. The fast inner loop handles altitude stabilization, while the slow outer loop handle navigation and altitude control. The building block of these loops is typically the PID controller, a robust compensator that adjusts with the output based on the proportional integral and derivatives of error signal. While PID is powerful and widely used tool, more advanced flight controller are also available. Techniques like linear quadratic regulator or LQR allows an engineer to design an optimal controller by balancing control effort against performance, while linear model predictive control or MCP can plan optimal control input over future time horizontal uh, future time horizontal, allowing it to handle complex constraint more efficiently. This finally brings us to the highest level of autonomy, motion planning. Once the drone can stabilize itself and follow command, it needs the intelligence to generate those commands on its own. Motion planning is the process of computing a collision-free path from starting point of goal. It's essential for navigating in complex military environment. Planner must be computationally efficient to run on the drones, limited hardware, and robust enough to handle dynamic environment sensor uncertainty. This can even be extended to highly specific tasks like the structural inspection, path planning. Here, the goal is not just to fly from A to B, but to compute a trajectory that keeps a sensor, like camera, oriented towards the surface to methodologically inspect for defects such as on the bridge or a wind turbine. In conclusion, an incredible capacity of modern autonomous drone are not the result of single breakdown, but rather the seamless integration of these many technological layers. It begins with a diverse suite of sensors providing a rich, multimodal view of the world. The raw data is then refined into coherent picture by sophisticated state estimate algorithm like the EKF. The clean state estimate is fed into hierarchical control system that provides robust stability and command following. And finally, intelligent motion planning algorithm use this capacity to make their own decision navigating complex world to achieve their mission goals. It, it is this complex stack from sensing to planning that truly define the state of art in advanced drone operation.